into it. So we're going to be starting with bivariate data. So briefly to review, what is bivariate data? Well, if we break it down, bi is meaning two. How I like to remember this, bi in bicycle, binoculars, we're always talking about two eyes, two wheels, we're talking about two. And then variate is referring to variables. So when we're looking at bivariate data, what actually is it? It's data with two variables. So we're going to have two lots of numbers that we're like measuring or recording. So examples of bivariate data, height and weight. They're two different variables, two different things that we're investigating. And then because we are looking at those two different things, we actually have the added bonus of now that we're looking at two different variables, we can actually also look at the relationship between these variables. Whereas when we only have univariate data, which is data with one variable, for example, just height, we have nothing to compare it to and we can't look at any relationships. That's when we more look at like mean, median, and mode when we only have that one variable. But when we have our bivariate data, that's when we can start to look at like correlation and creating a least squares regression line and all of that. Another one is temperature and ice cream sales. Again, if we record both the temperature on a given day and the number of ice cream sales, we can start to have a look at the relationship. So for example, when it's warmer, do we sell more or less ice cream? And we can start to have a look at what that relationship might look like. So again, the buzzwords, we're looking for patterns, associations, relationships. We're always interested in how are our two variables related. And there are multiple types of bivariate data as well. The first kind of distinction I want to make as well is the difference between the explanatory variable and the response variable. This is just terminology that could also pop up on a multiple choice question, but it is also really important and valuable for some of our further things when we start to look at scatter plots and correlations and everything as well. So what is the difference between the explanatory variable? The explanatory variable may explain the associated changes in the response variable. So we're looking at correlation, we're looking at the relationship between two things, but when we're deciding which we think is the explanatory variable, that's the one we think is causing the change, and the response variable is the one that we think is the one being influenced. So for example, in my temperature and ice cream sales example, I would say that temperature would be the explanatory variable and ice cream sales would be the response variable. And then if I put it into this sentence format, that helps it make like a little bit more sense. So like the variation in temperature may explain the associated changes in ice cream sales. So the changing temperature is what I think is causing the difference in my ice cream sales, which makes sense because on really hot days, you'd expect more people to be wanting to buy ice cream. The next is categorical variables. So when we think categorical variables, we're thinking categories: small, medium, large, yellow, blue. These are all categories, data that fits into different categories. Whereas on the other hand, we have numerical variables as well, which are any variables that give us like number results. So 1.7, 2, 26, 60,000, it could be anything. So a further way that we like class or kind of are able to identify numerical variables is by the fact that we normally like measure or record them. So for example, measuring height with a tape measure, like we measure it. So we know that it's going to be a numerical variable. Or if we're thinking about the number of trees in a forest, like we have to count it. So we know that again, it's going to be like that numerical variable. So, question, is the age of a car or the price of a car the response variable? You can have a think about that one. And our second one is height measured in centimeters a numerical or a categorical variable? So for the first question, I would definitely say price. Because again, when we think about what's the difference between an explanatory variable and a response variable, the explanatory variable is the one we think is driving the change, which here I think the age of the car would be what's affecting the price, and the response variable, kind of like the outcome, is the price. So if a car is older, that's going to probably cause it to be a bit cheaper. And if a car is a bit newer, that's probably going to be associated with a slightly higher price because it's a newer car. And our second one I would definitely say numerical, because we're measuring height in centimeters. So that's something we're having to like measure and count, so it's numerical. Another little difference there that I like to keep in mind is the idea that numerical data is often like continuous. So it can go on and on and on, like it might have decimals, it might have like countless options, but categorical data, like categorical variables, like it's a much more narrow range of like the options that we might have. So we normally have like a discrete and limited number of categories. Like, what is your favorite flavor of ice cream? And we might have like 5 options for people to choose from. So we have a discrete number of categories, which when we're thinking about the difference between numerical and categorical data, that has a lot of implications for like how we represent it and discuss it. So speaking of, the first thing that we have here is two-way frequency tables, which you may or may not be familiar with. So how a two-way frequency table works is the idea is that it goes 2 ways and it records the frequencies of our outcome. So we have one variable that goes this way and then one variable that goes this way. So each kind of number is representing a certain category. So here we're looking at like the explanatory variable we've said is gender, and we've said the response variable is like pet or like pet preferences. So here we're thinking that somebody's gender may explain their pet preference. And here we have some data that's been really neatly arranged in a two-way frequency table so that we can actually start to see if we think that may or may not be accurate. So we can see that out of the females we interviewed, 47 of them preferred cats, 17 preferred dogs, and out of the males in this imaginary sample, 39 preferred cats, and we had 64 males that preferred dogs. So from here, you can see we have a few blank squares in our table. So what we can actually do there is we can actually fill out the total columns. So for example, to figure out the total number of females that we interviewed, female total numbers, we'd add these together because the number of females that voted for cat and the number of females that voted for dog is going to add up to the total number. Same for males, total number of females, total number of males, and we can also calculate it across the rows. So total number of people that voted for cat and total number of people that voted for dog. So two-way frequency tables, what do we know about them? So they usually display categorical data. That's one thing I would like to draw your attention to. Don't be fooled by the numbers, 47, 17, 39, 64. Our variables are still categories. And so to illustrate that a little bit further, I'd like you to imagine if we were going to have a two-way frequency table for temperature, imagine all of the columns we would need. So if, for example, I pull up my laser again, if our explanatory variable was temperature, imagine if I had to have a column for 17.1, 17.2, all the way up to 29.1, 29.2, 29.3. I could, because numerical data is like continuous, and it's ongoing, I could literally have like almost an infinite amount of rows and categories, which just is not a helpful way to represent our data. But when we're looking at categorical data, remember that's our like discrete number of limited categories. We have like the benefit of, like I said, there's only that discrete number of limited categories. So it's actually a really nice way to represent this data. Here, for example, we only have female, male, cat, dog. We've got 2 variables and we only have 2 categorical options for each. So it's a lot easier to represent it this way. And again, while we do have numbers representing the amount of votes we had for each category, our variables themselves are gender and pet. And they're definitely categories because the categories we have in this scenario are female and male and cat and dog. And totals, like I said before, they can actually be expressed in either numbers or percentages. So what I mean by percentages is we can actually take the number and convert it to a percentage. And that actually allows us to compare like the numbers and the values on equal footing. Because at the moment, you can see that I've actually interviewed quite a lot more males than females. So it's actually not fair to say, well, 47 females prefer cats and 39 males prefer cats. So therefore, females prefer more cats. That's actually not a fair comparison because I've interviewed more males. So to remove the impact of that, we can actually calculate it as a relative percentage, and then we can compare the numbers in percentages. Because can you imagine if I'd interviewed 100 females and only 3 males? I would be able to say like, oh my goodness, like 80 females preferred cats and 0 males preferred cats. Like, look at this awesome data, but it's actually not awesome data because we haven't collected enough to be able to draw a reliable conclusion. So when we only do have these small sample sizes, or just even like varying sample sizes, to compare it on equal footing, we actually need to calculate percentages, which we're going to have a look at here. So you can see I've got our table here. Again, we've got female cat and dog votes, male cat and dog votes, and we've got the total. So we had 86 votes for cat and we had 81 votes for dog. But again, because we've interviewed different numbers of people, we're going to calculate like the relative percentage frequency so that we can kind of compare them on more equal footing. So you can calculate percentages going across for rows. So this would be 100% here and this would be 100% here. Or you can do it for the columns, in which case it'd add up to 100% this way and 100% this way. So what you're looking for depends on what your question is asking you. So here we're doing an example of calculating it for our rows. So we're going to calculate the percentage of females who prefer cats. The awesome thing about doing the percentages is it's just regularly how we calculate percentages. So we take the part, divide it by the whole, and that'll give us a decimal, and then we times it by 100 to get the percentage. So part is the number of females who prefer cats, which is 47. And then we divide it by whole, the total number of people that prefer cats, which here we can read from our table is 86. So we divide 47 by 86 and we multiply it by 100. And that gives us 55%. So now when I'm talking about the 100% of people who prefer cats, I can say that out of these people, I can say that 55% of the people who preferred cats were female. And then if I fill out the rest of my table, I'll have a lot more data I can discuss as well. So for example, here is an example of that table all filled out. So you can see that I've got 55% of the people who prefer cats are female, and then that leaves 45% of males who prefer cats. Because again, we know it's going to add up to a total of 100. So my options are either do this calculation again, so part over whole, 39 over 86 times 100 will give me 45%, or also because I know it's going to add up to 100%, sometimes I could just go, well, 100%, take 55%. I know it must be 45% of males that prefer cats, but sometimes with rounding errors, that's not the most reliable way to do it. So I'd still definitely recommend just always calculating it from scratch where possible. And then we've done the same for dogs, calculated out of the total number of people that like dogs, what percentage of them what percentage of those people are female and what percentage of those people are male. And now that we've calculated the percentages, we can actually compare these things on equal footing. And then from there, we can actually draw conclusions and answer a whole bunch of different question types about our data. And another hint that I have for you guys is when you're writing reports about data, I actually find the teal paragraph structure really helpful. I know it might sound like a bit of an English thing, but it can just be like a mental cue to help you to remember to make sure you're including all of the information. So T, topic sentence, what's your point? Are we saying that females are more likely to prefer cats or dogs? Are we saying males are more likely? What are we actually saying? So making your point and your stance. And then evidence. The most important thing when you're asked to like draw a conclusion is to actually give evidence. And if it's talking about evidence, it's probably talking about numbers from the table or the calculations that you had to do. So I want to see numbers in your answer. I want to see 55% in comparison to 45%. I want to see like you comparing all of these different numbers, and then explain if there's any other information you feel like you need to add to communicate what you're discussing. That's really important to make sure you communicate that as well. And then like a linking sentence if you want to summarize your point. So I just find that's a really helpful like cue in my mind to help like make sure that I'm remembering to include all the appropriate things. But you don't necessarily have to follow that structure, but as long as you remember to really clearly make your point and back it up with evidence from the table. So those two things are really, really important. And make sure you're actually answering the question. So you're not just summarizing the table, unless that's what you've been asked to do. You'll probably be asked to draw a specific conclusion about your two variables. So make sure you're always reading the question really carefully as well. So our two-way frequency tables, that's how we represent and make sense of our categorical data. So our discrete categories. So for example, the one we just looked at was like pets and gender. We only have a few discrete categories in each. So it made sense to represent it in a table. But this example here is an example of a scatter plot, which you might have looked at in class already. So scatter plots represent bivariate numerical data. So when we have two numerical variables, scatter plots are really awesome. Obviously, they represent this really well. Because again, coming back to my analogy like with a table, can you imagine if I had to have like a column or a row in my table for like 20,000 kilometers, for 35,000 kilometers, for 49,000 kilometers, for 161 and 743,000 kilometers. It just doesn't make any sense. It's not practical to represent this in a table. But that's where scatter plots come in super, super handy for representing bivariate numerical data, because it is ongoing, it's continuous, there's so many different possible variables. But by having this one axis with all of the numbers along it, we can actually plot every point. And every point has a corresponding value for our explanatory variable, which is along our x-axis, and our response variable, which is along our y-axis. So this car, for example, has driven about 265,000 kilometers, and it costs about $9,000 approximately. If I was going to check exactly, I could, but just by having this scatter plot, we can actually read off it and get a lot of information about it. So like I said, another really good thing about scatter plots is they're visual. We can see patterns, we can see trends, and then we can actually observe them and discuss them and see what do they actually mean. A few key things in scatter plots, make sure title is always really important. And again, we're usually talking about correlation in scatter plots. So I've called this correlation between kilometers traveled and price of 2012 Toyota Corollas. And it's just fairly standard form as well, that you put your explanatory variable on the axis down the bottom, and the response variable goes on your vertical axis, your y-axis. So here, kilometers traveled, I thought that was my explanatory variable, because I thought how many kilometers the car has traveled may explain like the change in the price of the car. Definitely not the only factor, but I definitely thought it might be a big factor. So this is how I put together my scatter plot. And you can start to see that we actually do have like a pattern. Patterns are just any overarching trends or any conclusion you can actually draw from your scatter plot. And so that's, a quick introduction to scatter plots. So there are lots and lots of different things we can actually talk about when we're discussing a scatter plot. The first thing we can talk about, is it a positive direction? Is it a negative direction? Or is there no association? All right, I don't know if I have a slide for that, but let's discuss what that means now. So direction, is it positive? Is it negative? Or is there no association? So what I'm seeing here is a overall decreasing direction. That's the trend that I'm seeing. So this scatter plot, I would say, has a negative direction. If it was going to have a positive direction, it would mean it would be moving up. So as one variable increases, the other one would be moving up. But that's actually not what we see here. We actually see that decreasing trend, which is our negative relationship. Of course, the other option is no association. So that's if our points were all kind of just randomly scattered about and there's not really any sense of direction to it. We'd say it has no association, because you can't have a positive or negative direction in that scenario. But here we have a negative direction. So we can see that that's telling me that as the kilometers traveled increases, the price of the car decreases. So that's what our negative relationship is. As one variable increases, the other variable decreases. Whereas in a positive relationship, as one increases, so does the other. And that's how we get that positive relationship. So again, whenever you're discussing a scatter plot, we're thinking direction, form, strength, and outliers. So direction, I've decided it's negative. Form, linear or non-linear. So linear is saying like it's forming like a linear pattern, like a straight line. Whereas non-linear, it could be like going like this, or it could be like changing directions, anything that's not in a straight line. This does appear to me to be a linear pattern because it does look like it's following a straight line for the most part of things. But there's some further statistical analysis, like a residual plot, that tells you a little bit more about that, and we'll get into that soon. So I'm going to say this is linear for now until I can see if it is by testing that out later. Strength, is it weak? Is it moderate? Is it strong? This is looking fairly strong, so I'd probably say like moderate to strong, because if it was weak, the points would be quite spread out. If it was strong, they'd be really close together. So, but there is definitely a fairly strong looking pattern there. So I'd say it's like a moderate to strong relationship. And I don't really see like any obvious outliers. Like, I mean, maybe that one, but not really. It still like generally falls in with our pattern. So if I was going to describe this, like I have on our next slide, I would say the scatter plot revealed, like I did say a moderate to strong. I said it was negative, and I said it was a linear association with no evident outliers. So when you're discussing the relationship between two variables, those are all of the key things that you want to be hitting on. But let's get a little bit more specific. I just estimated the strength of that scatter plot. I said it was like moderate to strong. That is incredibly vague, and it's only an estimate. So it's not a very specific way to discuss the strength of a correlation, which is where the correlation coefficient comes in. The correlation coefficient is an R value, which tells us the exact, precise mathematical strength of the relationship between these variables. And it's a very long process to calculate it by hand, which we won't be going through in this video, but it is something you'll definitely be covering in class. And yeah, it's very important to be familiar with that process. So what does an R value tell us? R values tell us the strength of a linear relationship, and they can range between -1 and 1. So -1 is a perfect negative relationship. So if we had like a little scatter plot here, a perfect negative correlation would be like a direct perfect negative correlation. And +1 would be a direct perfect positive correlation. If it's close to 0 in the middle, that means like all of our dots are like really randomly scattered around and we don't really have an association present. But you can start to see how like having this range and like the statistical process of calculating an R value, that's actually a really valuable thing because it can tell us the exact and precise mathematical strength of the relationship. But one thing I will show you is how to calculate this with a calculator. This is one of the most time-saving and helpful tricks I know. It certainly doesn't replace actually knowing the full process and how to calculate it, because there is a chance you'll need to apply that within an exam, for example. But if you're asked to calculate a correlation coefficient, for example, like a multiple choice question, or if you wanted to check your answer, being able to kind of do that on a calculator is such like a massive like time saver, and it's just like a very valuable trick to have in the back of your mind. But again, it doesn't substitute knowing the actual process. And my last hint before we get onto that is to be really familiar with your formula sheet, which I've linked in the slides, so you can go down and download those as well if you'd like to, because it's really, I can't stress enough how important it is to know what's on your formula sheet. It is a publicly available document. You're meant to be able to be familiar with it. And why it's like so important is so that you know what formulas are on there, and so that you know how to use the version that's on the formula sheet. Or if you don't like the specific version on the formula sheet, you'll know that you need to memorize the one that you prefer to use, so that you'll have that ready in your mind to use in the exam. And also, not all the formulas are on the formula sheet. So being very familiar of what's on there, do you know how to use it, and is that the version you want to be using? So get familiar with your formula sheet as well as the syllabus. They're like the most handy documents because they pretty much tell you they're designed to tell you what you need to know and how to approach it. So definitely find those ones. So this here, again, slides available to download. I definitely recommend you taking a photo or downloading the slides or jotting this down or giving it a try now on your calculator so you can have a practice of it. But yeah, this is how to calculate a correlation coefficient using your scientific calculator. So if you press mode, which should be a button on my calculator, it's in like the top right hand corner. If you press mode, it'll pop up with 3 options. What you want to do is press 2 for the stat mode, which will put your calculator into statistics mode, which changes it in some small way and is just part of the process of how you get to where you want to be, I suppose. And then you press 2, which will say A plus BX, which is referring to the fact that it's bivariate data. And then what you do is a little table will pop up and you enter your X and your Y values. So you might move around the grid using the arrows. You might go like, up and down, left and right, and you enter the number and then click enter. And then you enter your next number, click enter. Then you might need to use the arrows to move around to like the Y column, for example, until all of your X and Y values are entered. So you'll have a corresponding X and a corresponding Y value for each value. And then you press on, and this will clear your data, but don't stress. It's all part of the process, and the calculator does have it stored in its memory. The next few steps, you kind of do need to remember these ones a little bit as well. You press shift, and then you press 1, and then you press 5. And it'll come up, the option for 5 will say reg, and that's short for regression. And we're doing regression analysis. So that's the type of data analysis that we're doing. And then the option for 3 will be R, which is the correlation coefficient. So then you press 3 for R and then equals, and it will give you a correlation coefficient. If these little prompts don't pop up, you might have done something a little bit wrong along the way, so you might need to try that again potentially. But then as long as it gives you a number, and it should definitely be between -1 and 1, you'll know that that's giving you the correlation coefficient. So this massive time saver, I definitely recommend you learn this process, because for general maths, we get our calculators for both exams, which is just so beyond valuable and helpful. So definitely make the most of that. And then my last little tip is make sure you put your calculator back to the regular mode once you're done, just because the statistics mode can really mess with the settings a little bit. I don't exactly know how it works, but it is important to put it back into the regular mode. So you press mode again and then 1, which will say comp, and then to switch it back to the normal mode. And then if you need to do any more statistics calculations, you just again go back to the start, press mode 2, and it'll be back into statistics mode. So definitely take note of this. It's incredibly helpful. And again, if you have any issues with that, please let me know in the live chat and I'll be there available to help you out with that. And hopefully, get you on the right track with that, because it's a really, really helpful trick. Awesome. This is another really valuable resource. This is like a rough guide for how to interpret R values. So again, anything above 0 is going to be positive. The number is positive, means it's going to be a positive correlation, which reflected on a scatter plot means it's going to be moving up. Because again, positive means as this variable is increasing, this variable is increasing too. So that's positive. And the stronger it is, the more predictable the relationship is, the more strongly correlated they are. And again, anything below 0 is going to be negative. And again, as we get closer to -1, it's going to be a stronger negative, and as we get closer to 0, there's a weaker association or no association if it's around 0. So again, this is just a rough guide or chart of how to interpret R values, and then also what that looks like in a scatter plot, so you can kind of visually get an idea of what that looks like. And that brings us to a least squares regression line, which is kind of the next step in a regression analysis. So if you've heard of a line of best fit, you've kind of heard of a least squares regression line. So a least squares regression line is a mathematically precise line of best fit. So in a test before, especially when you were younger, you might have been asked to draw a line of best fit. You might have just taken a ruler or even just your pencil and just drawn a line through it, that estimated and roughly represented the overall trend. That's an awesome thing, but it's not mathematically precise. So the process of calculating a least squares regression line is how we get that to be more precise. And the formula of the structure of how we do that is y equals bx plus a, where y is our response variable, which we've discussed. B is the slope or the gradient. So this can be a little bit trickier to interpret. So the gradient, or B, estimates the average change in y, which is the response variable, for each 1 unit increase in the explanatory variable, which is x. And then A is the y-intercept, which is where the trend line or the line of best fit intercepts the y-axis. And the cool thing about that is that's always going to be when x is equal to 0. So that's kind of how you go about finding the y-intercept, because when x is equal to 0, so if, for example, I draw us a scatter plot example here, if, for example, our line of best fit looked like this, we can see that this here is where my line intercepts the y-axis. And that's really valuable to note because, well, first of all, because it's a part of our equation, but also because it tells us more about like our data. So we know that this point here is where it intersects. This is our this is our y-axis. So this is where our line intercepts our y-axis. Conveniently though, this is our x-axis, whatever our scale is, might be 0, 1, 2, 3, 4, 5. Where the line intercepts the y-axis, it's always going to be when x is equal to 0. So that's another cool little trick as well, if you're ever needing to calculate that. And then coming back to like the slope and the gradient, so that estimates the average change in the response variable for each 1 unit increase in the explanatory variable, or like the x in the case of the formula. So here, for every 1 unit increase, we have in the x, which is again explanatory variable plotted along this axis, what's happening to our response variable. So in this one, we can see that with each 1 unit increase, our response variable is also increasing. So here you can see we're going to have a positive slope or gradient. It's going to slowly increase because for every increase we have in x, we also see an increase in y. Whereas, for example, if I had a negative line, for every increase in x, we're going to have a decrease in y. Increase, we're going to decrease, decrease, decrease. So it depends what type of like trend pattern relationship that we're looking at. But that is a quick overview of how to interpret the least squares regression line. So here you can see I've got an example. You can see that I've got y, so my response variable, which here is the price of the car. So here I'm saying the price of the car is equal to negative 0.0406 multiplied by the kilometers traveled plus 17,643. So you can see if my line was to continue up and intercept the y-axis, and you can also see x is equal to 0, the value that's going to be there is about 17,643. So that's using my line to predict what the price of a car is when x is equal to 0. So when it's traveled 0 kilometers, this line's predicting the price of a new car. But again, extrapolation isn't always super reliable for a lot of reasons, which we're going to touch on a little bit later. And then we can also see that for every 1 unit increase, so for every extra kilometer the car travels, the price of the car is dropping by about 4 cents. So that's how I'd interpret this here. Well, that could be 0.04 cents. It depends on the unit we've used. Probably 4 cents, I think, if I am interpreting that correctly. But again, it's negative. So for every 1 unit increase, my response variable is dropping. So for every kilometer the car travels, it drops in value. The price of it drops, which makes sense because that's the kind of relationship that we're looking at. So again, calculating A and B by hand, bit of a time-consuming and painful process, but also really important. But you can also calculate this using your calculator. But again, it's not a substitute for knowing how to use the formulas in your formula sheet, because that's a really important part and could definitely be assessed on your exam as well. So similar process, mode 2 puts it into statistics mode. Then you press 2, which again is to get up that bivariate data table. You enter your values. Again, you press on, you press shift 1, 5. Again, same process as before to get into like regression, I believe. And then you can choose. 1 will give you the value for A, and 2 will give you the value for B. And then you can go back and do the process again if you want to find the other value. So you can also use your calculator to find A and B. Again, really helpful information to tuck away in the back of your mind. Another thing I'd love to touch on is the difference between like association and causation. The biggest and the most important takeaway from here is that correlation does not imply causation. So for example, if there was, if some random study found a massive correlation between divorce rates and margarine consumption, should we conclude that consuming margarine causes divorce? No, like that's a completely illogical conclusion. There are actually multiple non-causal explanations for an association. And the other thing to consider as well is if it was a really small sample size, like it might actually be like a fluke, which is actually one of the explanations we're going to look at as well. So the first one, common response, when two variables are strongly associated because they are both strongly associated with a third common lurking variable. So this is where general maths isn't black and white using formulas. It's actually, you've got to do like a bit of like thinking, which is why I find it quite interesting. So for example, scenario, if a study found a really strong association between like the number of scarves worn and the number of hot chocolates sold, does that mean the number of scarves worn and the number of hot chocolates sold are like directly correlated? Well, no, it actually doesn't. There could be a third like lurking common response variable, such as the temperature. So in this scenario, the temperature is associated with the number of scarves worn, and the temperature is associated with the number of hot chocolates being sold, because if it's colder, people will wear more scarves and buy more hot chocolates, which has made it seem like scarves and hot chocolates are correlated, but they're actually not. It's actually that lurking variable. Another one, confounding variables, where there are actually two possible causal explanations. An interesting example of this is crime and unemployment. When we look at like that, like sociologically, does crime drive people to unemployment, or does unemployment drive people to crime? Interesting. Which way does it go? How can we know? Another really interesting thing is when we're only doing like observational studies or correlational studies, when we're just like observing and collecting data, we can never actually talk about causation. We can only talk about correlation and association. To be able to talk about like causation, you have to conduct an experiment, which is where you like directly choose to manipulate a variable, which is something you might have looked at in science before. But we're only looking at association and correlation, so we can't be talking about causation. And like we touched on before, it could also just be a coincidence. Maybe their sample size was too small. Maybe the specific sample they looked at had this like correlation going on, but maybe it doesn't hold true for everywhere. Like it's just, sometimes it is actually just a coincidence.